I am the CEO of Qunnect, and Qunnect is a company located in the Brooklyn Navy Yard, which innovates devices to transform existing telecom infrastructure into scalable quantum secure networks. And I underline scalable because that's something that we really focus on as a team. And you'll see that reflected in our product suite. So Qunnect launched the first commercial memory to be launched globally, we think, actually in September of 2021. It's shown here as the large rack mount unit that you see here. And it requires no external cooling or vacuum support. Why is this significant? Well, it's because when you start talking about quantum networking, one of the things that you need to consider is the fact that all of the equipment is going to be scattered along unmanned stations and fiber hubs, where they need to be extremely robust and cannot have very delicate types of equipment like cryogenics and vacuum support, which are also energy intensive, actually scattered every 25 to 50 kilometers. So we've spent a lot of time as an organization thinking about how we can turn this innovation into something which actually supports quantum networking protocols. And the protocol that we're interested in supporting is called entanglement swapping. So for those of you who are following the Nobel Prize this year, there were a number of great articles that came out about entanglement and entanglement swapping. So entanglement swapping is the concept of taking pairs of photons which have never met each other, interfering one half of each one of those entangled pairs, and actually transferring information to the remaining two photons, one from each pair, onto the same mapped entanglement state. And what you need in order to do that are devices like the source that I have here with the little infinity sign, which produces a pair of photons. One goes to a swapping station from either side. You perform a Bell state measurement in the swapping station. And when you do so, the photons which remain from the two pairs that originated at the sources are now mapped onto the same entanglement state. Well, the problem is you'd like to be able to do something with them. And that's where quantum memories come in. So quantum memories were thought for quite some time now to be the sort of key enabling device to go towards what we all think of as a quantum repeater. And a quantum repeater, analogously, just to the same way that we think of digital repeaters, is a way to actually increase the distance over which you can distribute entangled pairs of photons over what we think of now like a normal network. And for those applications like what Mark just mentioned, of quantum memories and quantum sensor nets, quantum computing, distributed quantum computing, and distributed quantum sensor nets, you need to be able to hold onto the photons so on demand you can actually give them to other parts of the network to do something. So Qunnect again launched this memory in September of 2021. But then we also realized that what we needed to do was to be able to support that with something that had very low interfacial loss to the memory in order to have something that, again, works well in the network. And that's how we came to the point of developing the rest of our product suite. So one of those devices is the source. So again, the source and the swapping station are necessary to be able to support entanglement swapping. The memory is there to be able to temporally control photons and do something with them later in the downstream protocol. And our source is a source which is based on spontaneous four-wave mixing. And right now is the only source on the market that is producing narrow line width photons, which has something to do with those interfacial losses that I mentioned. Ours is tunable from 50 to 500 megahertz. And we produce very high quality pairs of polarization entangled qubits at over 100 kilohertz in rate. But this isn't enough because the problem is you want to do this over real infrastructure. And when you do that, you start to realize that what you actually need are local references and calibration tools in order to be able to make a network-wide system viable. So in order to do that, Qunnect came up with another series of instruments that we call these quantum support instruments. One of them is a very good wavelength reference that sits at every node. It's atomic based, similar to the fact that the memory and the source for Qunnect are also atomic based. You need a clock to be able to distribute the same timing reference across your network with extremely high precision, so sub-nanosecond. And that was the original role of QSync, but now QSync has evolved into something which also controls the other devices within our product suite. And then finally, you need to deal with the fact that sending data through real-world fiber is hard. And for Qunnect, which at present we use polarization qubits in all of our protocols, that requires us to have something that goes out and actually tests any fiber channel that you're going to use in real time for the types of polarization drift which are experienced by environmental perturbations and corrects for it. So again, just to roll through some of these challenges when you decide to take stuff out of the lab and put it into the real world, Qunnect is actually trying to do this like in the extreme. So as Mark mentioned before, we just closed our first funding round. Part of that funding round is intended to support a quantum network testbed being built in New York City. It is the orange loop that you see here originating from Qunnect headquarters and going through Brooklyn and Queens. I've put for scale the island of Manhattan next to it from Google Earth, so you can get a sense that this is like half the size of Manhattan. So significant in terms of distances. And if we can do it here, I can tell you that we can probably do quantum networking almost anywhere because it's old infrastructure patched together, obviously never intended to host something like quantum information. So to review some of the major challenges, specialty cooling and vacuum is simply not practical for real world scalability. It doesn't mean it's not going to be out there, and it doesn't mean that it's not going to be in hybrid systems where you have long-term storage nodes and interfacing to computers, et cetera. However, if you need to put stuff every 25 to 50 kilometers, it's not going to be practical. If you are still going to do that, then you have to have instruments that also don't need somebody to tune them every 5 minutes. So instruments must be low maintenance and they have to be stable. That's hard for quantum equipment because everything requires high precision, at least in terms of photonics and optics. You also need to start focusing a lot on what inter-instrument losses are or network to instrument losses are, because they compound very quickly in your network if you're talking about lots of nodes. So again, real world fiber was not meant to host quantum information. So one of the problems is that environmental perturbations like rush hour, or going through an aerial segment of fiber, which is flapping in the wind, or going underneath water, all of this has the tendency to actually change the birefringence in the fiber itself. So you need some way to compensate for that. And then, of course, the precision of quantum systems demand accurate local references, which is exactly why Qunnect's product suite in the second half of the products I showed you is all focused around the fact that you would like to have a solid wavelength reference at every node. You would like to have a solid timing reference at every node. And one reason you want those solid wavelength references is that the lasers which drive all of your equipment need to be locked to something. And right now, the OEM lasers at quantum-friendly wavelengths simply don't exist. So this is an open problem. That's something that's near and dear to Mark Whippich and the QED-C, who've developed a tool to try to gather information on the most used wavelengths across the field in different physical systems. So what we're doing at Qunnect is really pushing forward this idea of a necessity for being able to have real-time polarization compensation on networks. Is something which is good for QKD networks, is something which is good for time-bin qubit networks, and it's something which is good for polarization qubit networks. So it's effectively qubit agnostic. We've designed something with a very minimal insertion loss of less than 2 dB. There's very fast measurement and compensation across very noisy fiber lines, which we've driven this on already. We are agnostic to which telecom band you would like to use this in. And it can be triggered via either setting a threshold or setting a schedule or actually just requesting something on demand. But to give you an idea of how it works, here's a noise spectrum with a certain types of frequency, which are those perturbations which are happening in any given fiber line. You can see the drift is something that looks like a big mess here, where the fidelity drops from what was 100% down to something as low as 50% within 6 minutes and fluctuates around these different things. When you click this instrument on and you say, I want to maintain a threshold, in this case of 95 or 94% or above, it actually locks the polarization at a level which is above that and continues to sample and try to maintain the polarization above it. And why this is important is because if you are trying to do any type of quantum transaction over fiber and things have now drifted in polarization and you're trying to now interfere 2 polarization qubits, you simply can't do it. So this is something we think is going to be very important to support quantum testbeds going forward. And we would like to get out there. So we are seeking customers for these instruments and partnerships. If you're interested in working with us, this is something that is ready to go and has been tested on several other fiber networks in New York State. We also are seeking partnerships with some of our other instrumentation. As I mentioned before, Qunnect just closed on $8 million, led by Airbus Ventures, Sandbox IQ, and Quantination also are significant participants in that. We are also seeking contract manufacturer intros for specialty optics assemblies. So many of our instruments, as you've seen in the CAD renderings, which I showed, look like research instruments because they are research instruments. We want to turn these into products. And products means that they have a good software interface to the world which we want to use them, which is the networking world. So we have job openings for software developers, EEs, optical engineers, etc. And if you would like to join us, we are currently a team of 12. We're hoping to grow to a team of 18 over the next few months. And just drop me an email on our contact @, and we look forward to hearing from you.